Welcome to the Deep Dive. Today we are swapping the blueprints of aerospace engineering for, well, something pretty amazing from the ocean floor. The peacock mantis, shrimp.
Yeah, it's quite a shift. Usually when you think about impact resistance, damage tolerance,
Yeah.
you're thinking advanced composites, maybe metals.
Exactly. Carbon fiber, titanium alloys, that kind of thing. But it turns out nature might have beaten us to it with this little crustacean.
Oh, absolutely. The peacock mantis shrimp Odontodactylus cillaris is its fancy name. It's only a few inches long, but it packs this incredible punch with its dactyl club.
It's hammer, basically.
Its hammer, yeah. And it's this total engineering paradox. It hits hard enough to smash snail shells, crab shells, thousands and thousands of times, super high velocity.
But the hammer itself doesn't break.
Exactly. It survives intact. It's incredibly destructive, but also perfectly designed for damage tolerance. It's like self-healing armor almost.
Right. So our sources today really dig into this. We're looking at studies that literally dissected this tiny hammer, analyzed the crazy physics of the strike.
And then the crucial part, trying to learn from it, translating those biological design principles into, materials we can use.
Okay, so the mission for you, our listener, is to really unpack this. We want to look at the research, figure out the engineering blueprint hidden in this shrimp's weapon.
We're pulling from studies covering the microscopic structure, the material science, the extreme physics, and even some pretty sophisticated computer modeling. Finite element stuff.
Simulating the attack itself. Wow.
Yeah, trying to figure out the optimal way it hits.
Okay, so the main takeaway, the core insight we're aiming for, is how nature uses structural tricks, specifically this unique spiraling fiber pattern.
The helicoidal structure, yeah.
How that can help us make next-gen composites.
Yeah.
Materials for aerospace, cars, maybe even armor. Things that are tougher, definitely.
But more than just tough. The key is residual strength. What happens after it gets hit? That's the holy grail here. Making things that don't just survive, but keep working reliably.
Right, not just taking the hit, but staying strong afterwards. Okay, let's get into it.
Wow.
All right, let's start with the weapon itself, this dactyl club. You mentioned it smashes shells. These are tough materials in their own right.
Absolutely. Gastropod shells, crab shells. They're composite materials, too, highly optimized by their evolution to resist being broken.
Okay.
So the mantis shrimp is in this constant arms race.
It needed something incredibly powerful.
Exactly. And the demands are huge. To deliver that crushing blow, you need something stiff and hard to transfer the momentum effectively.
It makes sense, like a good hammerhead.
But if it's only hard and stiff, like ceramic, well, the first time you hit something really hard, whack, it shatters.
Right, brittle failure. Been there with coffee mugs.
Precisely. So the evolutionary puzzle was, how do you make something stiff enough to hit hard, but tough enough to absorb the rebound, the reaction force, without just falling apart?
And the answer wasn't just one material.
No way. It's a multi-regional structure. The cuticle, the outer shell of the club, has different layers, different properties, all working together. It's like graded armor.
Okay, let's peel back those layers. Start with the outside, the bit that actually makes contact.
Right. That's the excuticle, the impact region. It's the outermost layer, wraps around the whole club, but it's thickest right on the striking surface.
And what's it made of?
It's a composite itself. The base is alpha-chitin. That's a structural fiber, kind of like cellulose, common in insects and crustaceans.
It's okay, flexible-ish.
Provides the framework. But then it's heavily mineralized with crystalline hydroxyapatite.
Hydroxyapatite. That sounds familiar. Like, bones.
Teeth. Exactly. It's basically a calcium phosphate mineral. Very hard, very stiff. So you blend the stiff ceramic-like mineral with the chitin fibers.
And you get something really hard and stiff, perfect for smashing.
Perfect for initiating fracture in the prey shell, yeah. And maximizing momentum transfer. This layer is all about hardness and stiffness, taking that initial massive stress spike.
Okay, so that's the hammerhead. Super stiff. But what stops it from cracking or just peeling off the rest of the club on impact? There has to be something underneath.
There is. That's the job of the endocuticle. Think of it as the internal shock absorber. It lies right beneath the excuticle.
And it's different.
Yeah, it's generally softer. It's mineralized too, but with amorphous, non-crystalline calcium carbonate and calcium phosphate. Its main role is energy dissipation, not stiffness.
Got it. And within this endocuticle, you mentioned specialized regions.
Two key ones. First, there's the striated region. This is interesting. It's made of aligned fiber layers that form a band running around the side of the club circumferentially.
Aligned fibers.
Yeah.
Like a belt. What's that for?
Think of it like a girdle, yeah. During that massive impact, the club wants to bulge outwards, right? Expand sideways.
Yeah, Poisson's effect.
Exactly. That lateral expansion could cause shear failure. So this striated band basically contains the structure, prevents it from bulging and failing that way.
Smart. Okay, what's the second region? You said that's where the real magic happens.
Ah, yes. The periodic region. This lies directly under the main impact surface, beneath the executicle. This is the core of the club's toughness and damage resistance.
This is where we find that spiral pattern.
This is where we find the helicoidal architecture, also known as Boulogne geometry. It's really quite beautiful structurally.
Okay, explain this helicoidal thing for listeners maybe not familiar. How does this structure work, and why is it so good at stopping damage?
Okay, imagine you're stacking layers of fibers like sheets of paper, but the fibers are mineralized to kin. In a normal composite, you might lay them all the same way, or maybe at 0 and 90 degrees.
Right, standard layup.
Here, each layer of fibers is rotated by a small, consistent angle relative to the layer below it. Maybe 10 degrees, maybe less.
So layer 1 is at 0 degrees, layer 2 at 10, layer 3 at 20, and so on.
Exactly. And you keep stacking and rotating until the fibers have twisted through a full 180 degrees. Across the thickness of this region, you get this continuous rotation.
Like a spiral staircase. Or looking down the threads of a screw.
That's a great analogy, a very, very tightly packed spiral staircase. If you cut it and look at the cross-section under a microscope, you see these beautiful nested arc patterns.
Okay, visually cool, but functionally, what happens when a crack tries to form in that? From, say, hitting a really hard shell.
This is the genius part. Cracks want to follow the path of least resistance, right? Which is usually along the interface between layers or fibers.
Makes sense.
But here, the fiber direction is constantly changing, so a crack starts, tries to follow the fibers in one layer, but then bam, it hits the next layer where the fibers are pointing slightly differently.
So it has to turn.
It's forced to turn. It has to constantly twist and rotate to follow that changing fiber orientation. It can't just zip straight through the material.
So instead of a clean, straight fracture, which is catastrophic failure, the crack path becomes incredibly complex and long.
Exactly. It dramatically increases the fracture path length. The crack is forced to spread out laterally, dissipate its energy over a much larger area. It gets arrested.
How does it dissipate the energy? Just by turning.
Turning is part of it, but also things like fiber bridging, where fibers span the crack and fiber pull out. Basically, it takes a lot more energy to make the crack grow through this twisted structure. It stops through thickness damage.
Which is the killer for standard composites, right? Delamination, layers separating deep inside.
Precisely. This helicoidal design is incredibly effective at preventing that.
Now, the research mentions something specific of the pitch lengths. That's the distance it takes for the fibers to rotate the full 180 degrees.
That's right. And they compared the peacock mantis shrimp Ocellaris, which is a specialist smasher, with other crustaceans like the American lobster, which is more of a crusher.
Smashers versus crushers. What's the difference in strategy?
Smashers, like our mantis shrimp, use high-velocity, short-duration impacts. Think hammering. Crushers, like the lobster, apply force more slowly over a longer time, like using pliers.
Okay, different needs. And how did their pitch lengths compare?
The difference was huge and really revealing. The smashing mantis shrimp has a very large pitch length in its periodic region, especially near the surface. Up to 115 micrometers, sometimes even more.
115 microns. How does that compare to the lobster?
The lobster's pitch is much smaller, typically between 6 and 35 micrometers.
Wow, that's a massive difference. So a larger pitch means the angle of rotation between each layer must be smaller.
Exactly. To cover 180 degrees over a longer distance, each individual step, each rotation between layers has to be smaller, maybe just a few degrees per layer.
And why is that small angle, that large pitch, so important for the shrimp's high-speed hammering?
It seems to maximize what's called in-plane energy dissipation. When you get hit really hard and fast right at the surface, you generate huge shear stresses.
Okay.
A small rotation angle, long pitch, is apparently optimal for spreading that stress out sideways within the plane of the layer before the crack even gets a chance to dive deeper.
So it makes the surface itself incredibly tough against that initial shockwave.
Exactly. The mantis shrimp needs maximum surface toughness to survive thousands of these violent impacts. And its structure, this large pitch, it's perfectly tuned for that, and it's not even constant.
What do you?
The pitch actually changes through the thickness. There's a pitch gradient. It's smallest angle, largest pitch near the outside, getting slightly larger angle, shorter pitch, deeper in. It's optimizing layer by layer.
Wow. Evolution really fine-tuned this thing.
Yeah.
Okay, so the club itself is this amazing piece of defensive engineering, built to last. Now let's flip to the offense. The strike itself, you said the speeds are extreme.
Extreme is putting it mildly for a biological system. We're talking speeds over 20 meters per second. That's faster than a speeding bullet underwater almost.
How does it even do that? Muscles alone can't.
No, it uses a power amplification system, like a catapult or a spring latch mechanism in its arm. It stores elastic energy and releases it suddenly.
Okay. And the acceleration.
Get this. Over 100,000 meters per second squared. That's $105 Tixo to Tex-22. Roughly 10,000 times the force of gravity, 10,000 Gs.
That's astronomical. And the whole strike is over in milliseconds.
Just a few milliseconds, yeah. Very different from a slow, crushing force. It's pure impact dynamics.
And the research found something surprising about this impact, didn't they? It's not just one hit.
That was one of the biggest discoveries. Each strike is actually two distinct, high-force peaks delivered in incredibly rapid succession.
2 hits for the price of 1 swing. How?
Well, the first peak is what you'd expect, the limb impact force. That's the balactal club physically hitting the target.
The hammer blow. How strong is that?
It's immense, consistently measured between 400 newtons, sometimes spiking up to over 1,500 newtons.
1,500 N for an animal a few inches long. That's thousands of times its body weight focused on that tiny club tip.
Insane forces, but then just fractions of a millisecond later comes the second peak.
Okay, what causes that? It's not hitting again.
No, the second peak is caused by cavitation.
Cavitation, like from propellers, bubbles.
Exactly like that, but weaponized. The club moves so incredibly fast through the water that the pressure right behind or around it drops dramatically, so low, in fact.
That the water boils, even though it's not hot.
Precisely. The pressure drops below the vapor pressure of water, and it instantaneously flashes into vapor, forming bubbles, cavitation bubbles, right near the impact site.
Okay, so it creates bubbles with the swing. How does that create a force?
The bubbles don't last. Almost as soon as they form, the surrounding higher pressure water rushes in, and they violently collapse or implode.
Ah, the collapse.
Yes. And this collapse happens typically around 390 to 480 microseconds after the initial physical impact, so less than half a millisecond later.
Tiny delay. And the collapse releases energy.
A lot of energy. It generates powerful shock waves and tiny high-speed water jets, microjets, directed right at the target surface. This implosion creates the second measured force peak.
How strong is that second cavitation peak?
It can be really significant. The study found it reached up to 504 newtons. On average, maybe around 50% of the main limb impact force.
So half the force of the main hit, delivered almost instantly after as a shockwave. That's quite a follow-up punch.
It is. But here's the kicker. Sometimes, under certain conditions they measured, the force from the cavitation bubble collapse actually exceeded the physical limb impact force.
Wow, wait. The bubble collapse was stronger than the actual hammer blow. By how much?
In some cases, up to 280% stronger.
That's unbelievable. So this isn't just some side effect of going fast. The cavitation seems like a planned, crucial part of the attack.
It really looks that way. The energy from the collapse is intensely focused, right where the initial impact just happened. It's like hitting a nail, then immediately hitting it again with a shockwave.
So the physical hit might initiate a crack or weaken the shell.
And the cavitation shockwave comes right behind it to exploit that weakness, drive the crack deeper, or cause more damage.
Did they have other proof it was cavitation?
Yeah, they looked at the sound signature. The second peak produced this broadband acoustic signal, lots of noise extending way up into the ultrasonic range, above 20 kilohertz.
And that's a classic sign of...
A definitive signature of cavitation bubble collapse. So the physics lined up perfectly.
So the mantis shrimp strategy is this potent 1-2 punch. Massive physical impact followed almost instantly by a powerful implosive force from cavitation.
Exactly. A combination designed to break complex composite shells that might resist just a single hit.
And it has 2 of these clubs, right? So it could potentially land 4 of these peaks in rapid succession if it uses both arms.
Potentially, yes. It's an incredibly effective hammering strategy, leveraging both mechanics and fluid dynamics.
Okay, so we've got this amazing biological blueprint, the helicoidal structure for defense, the dual impact strike for offense. Now, the big question, can we copy it? Can we actually engineer materials that mimic that structure?
That was exactly the next step in the research we looked at, trying to translate that Boulogne geometry, that helicoidal layup, into engineering materials.
What materials did they use? Did they try to make artificial chitin?
No, nothing quite that exotic. They went with something much more common in high-performance engineering: carbon fiber epoxy composites.
Ah, okay. Why carbon fiber?
Well, it's a natural fit, really. Carbon fiber composites are already made by stacking layers or plies of fibers embedded in a resin, usually epoxy, so the basic manufacturing process is already there.
You just have to control the angle of each layer very precisely.
Exactly. Instead of the standard 0, 90 plus minus 45 degrees, you program the machine to rotate each ply by a specific small angle relative to the one below it.
Got it. Now, to know if it worked, they needed something to compare it against, right? Controls.
Absolutely critical. They use two main control groups. First, simple unidirectional panels, all fibers lined up in one direction.
Okay, strong in one way, weak in others.
Yeah.
Basic benchmark.
Right. More importantly, they used quasi-isotropic panels.
Quasi-isotropic. That sounds familiar. You mentioned that's kind of the industry standard for things like aircraft parts.
It is. It uses a specific layup sequence, usually repeating layers at 0 degrees, plus 45, negative 45, and 90 degrees. The goal is to get balanced stiffness and strength in all directions within the plane of material.
So it's designed to be generally good all around. That's the benchmark they had to beat.
That's the one. If the helicoidal design can outperform quasi-isotropic, then you've really got something.
Okay, and how did they make the helicoidal test panels? Did they try different rotation angles?
Yes, they fabricated 3 different types, varying the angle between successive plies, but keeping it consistent within each panel type.
What were the angles?
They had a small angle group with only 7.8 degrees rotation between layers, a medium angle group at 16.3 degrees, and a large angle group at 25.7 degrees.
Why those specific numbers?
They were chosen carefully to ensure the final panel was symmetric about its midplane. That's really important in composite manufacturing to avoid warping when it cures.
Ah, practical engineering constraints. Okay, so they have the panels,
Okay.
unidirectional, quasi-isotropic, the standard,
Yeah.
and 3 types of helicoidal. What did they do to them?
They hit them hard. They used a standard test called the ASTM D7136 drop weight impact test. Basically, dropping a heavy weight from a specific height to deliver a controlled amount of impact energy.
How much energy?
100 joules in this case. Enough to simulate significant impact, like maybe a tool dropped on an aircraft wing or potentially a bird strike scenario.
Okay, so they damaged the panels, but you said earlier just surviving isn't enough. The key is what happens after the impact.
Precisely. The crucial measurement is residual strength. After the impact damage, they take the panels and test how much load they can still carry before failing completely. Specifically, they used a compression after impact CAI test, another ASTM standard, D7173.
Compression after impact. So you hit it, then you squeeze it until it breaks and see how much squeezing it could take.
That's the gist of it, yes. In aerospace, for example, a wing skin needs to carry compressive loads. If it gets damaged by impact, how much of that compressive strength does it retain? That's residual strength.
And high residual strength means?
It means the structure might be damaged, but it can still safely carry its operational loads. It allows for damage tolerance, safe operation until repairs can be made. Low residual strength means the initial impact damage could lead to catastrophic failure under normal loads.
Okay, that's clearly the critical metric. So what did they find? Let's start with the visible damage from the 100 joule impact.
The helicoidal panels looked better right away. They measured the depth of the dent on the impacted surface. Compared to the standard quasi-isotropic panels, the helicoidal ones had, on average, a 49% reduction in indent depth.
Wow, almost half the dent depth, so they resisted the initial penetration better.
Yes, but the really critical stuff is often internal, hidden damage. Delamination, the layers separating inside.
Right, you can't always see that from the outside. How did they check for that?
Using ultrasonic C-scans, it's like an ultrasound for materials. It maps out internal flaws.
And what did the C-scans show?
This is where the helicoidal structure really shone. The quasi-isotropic panels showed the largest internal damage area, the most widespread delamination.
Okay, the standard stuff got messed up inside.
But in the helicoidal panels, the extent of that internal damage decreased as the rotation angle between the layers increased. The large angle helicoidal panels had significantly smaller delamination zones.
So the twisted structure really did stop the damage from spreading through the thickness.
It absolutely did. It forced the damage to spread out more in plane within the layers rather than punching straight through, just like we saw in the mantis shrimp club's biology.
Okay, less denting, smaller internal damage. This is sounding very good. But did it translate to the big payoff higher residual strength in the CAI test?
It did, and significantly so. Compared to the quasi-isotropic control panels, the industry standard, remember?
Yeah.
The medium angle, 16.3-degree helicoidal panels showed a 16% increase in residual compressive strength after impact.
16%. That's a serious improvement.
And the large angle, 25.7-degree panels did even better, an 18% increase in residual strength.
18% higher strength after taking a significant hit. That's not just incremental. That feels like a step change for composite performance.
It really is. Gains like that often require developing entirely new types of carbon fiber or new resins. Here, they got it just by changing the layup geometry, mimicking the shrimp.
Using standard, off-the-shelf carbon fiber and epoxy.
Exactly. That's what makes this so potentially powerful for real-world applications. It's an architectural solution, not just a materials one.
Okay, but what about the small angle panels? The 7.8-degree ones. You said the managed shrimp uses small angles near its impact surface. How did those perform?
Ah, yes, the anomaly. They actually performed poorly in the CAI test. Their residual strength was down by 13% compared to the quasi-isotropic control.
Down. Why would the angle supposedly optimized by nature do worse in the engineered version?
This highlights a really important challenge in biomimicry. The researchers believe the main reason was edge effects in the test setup. The way the panels were clamped during the compression test caused cracking to start at the edges, especially in those small angle panels.
Okay, so maybe an artifact of the test.
Likely, yes. But it also points to something fundamental. Remember, the shrimp's club isn't just the periodic region.
Right, it has the hard executical shell and that striated region acting like a girdle.
Exactly. The small angle structure might be fantastic at dissipating energy in plane, spreading it sideways, which is great right at the impact point, but in the engineered panel without that confining outer structure and girdle.
When you compress the whole damaged panel, maybe that sideways spreading leads to failure at the free edges.
That seems to be the idea. The biological system is integrated. The small angle region works because it's contained and supported by the other layers. You can't always just copy one piece and expect it to work the same way in isolation.
So the lesson isn't that small angles are bad, but that context matters. Maybe the ideal engineered structure also needs that kind of containment, or perhaps a gradient like the shrimp uses.
Precisely. The shrimp uses a pitch gradient, remember. Smallest angle near the surface for toughness, perhaps slightly larger angles deeper down for overall stability.
Yeah.
Replicating that complexity is the next challenge.
Okay, we've deep dived into the club's defense, the helicoidal structure. But the research didn't stop there. They also looked at the attack strategy, that double impact from the limb and the cavitation.
Right. They asked a really interesting question. Is that double hit actually the most damaging way to deliver energy, or is it just a consequence of moving fast? Could a single, stronger hit be better?
How do you even test that experimentally? Seems tricky.
Very tricky. So they turned to computer simulations, finite element analysis, or FEA.
Okay, building a virtual model of the impact.
Exactly. They modeled a projectile hitting a target plate. The goal was to see how different impact sequences affected the damage to the plate, keeping the total energy delivered constant.
What was the total energy?
Quite small, actually 2.27 joules. They wanted to simulate the kind of energy involved in the shrimp's actual strike.
And the target plate, what was that supposed to represent?
It was modeled as an elastic plastic material, using the properties of aluminum as a reasonable stand-in for the general stiffness and behavior of a prey's shell.
Okay. And the projectile?
They used rigid spheres of different sizes, 3 millimeters, 4 millimeters, and 6 millimeters in diameter, to approximate the size of the shrimp's dactyl heel, which is around 4 millimeter.
So what variables did they play with in these simulations?
Quite a few. They compared a single hit delivering all 2.27 J at once versus multiple hits, double or triple impacts, splitting that energy.
And for the multiple hits, did they vary how the energy was split?
Yes. For double hits, they tried equal energy per hit, a strong first hit followed by a weak second, strong weak, and the reverse, weak strong.
And crucially, the timing.
Yes, they varied the time delay, delta T, between the consecutive impacts in the multiple hit scenarios, ranging from 0 milliseconds simultaneous up to 0.8 milliseconds.
Okay, lots of combinations.
Yeah.
What were the big picture findings?
Yeah.
Overall, what caused the most damage?
Well, perhaps unsurprisingly, if you just want maximum damage from a single event, concentrating all the energy into one single impact was generally the most effective configuration.
Makes sense. One big whack.
Right. Maximum instantaneous stress. Also, regarding the projectile size,
Which size did the most damage?
the smallest one, the 3 millimeter sphere.
Why is that?
It lines up with basic contact mechanics, often called Hertzian stress. Applying a same force over a smaller area creates much higher pressure. Higher pressure means better penetration and more localized damage.
So smaller is punchier, and the biggest one.
The 6 mm projectile caused the least damage, spreading the force out more.
Okay, but the shrimp's heel is about 4 millimeters, so they focused on that size.
Exactly. The 4 mm projectile was interesting because it often caused partial damage. In the simulations, it didn't necessarily punch right through, but it definitely damaged the plate. This felt like the most realistic scenario for the shrimp trying to crack a tough shell.
So focusing on that 4 millimeter projectile and the double impact scenarios, which specific combination, energy split, and timing turned out to be the most effective at causing damage?
This is where it got really interesting and connected back to the biology perfectly. The simulation that maximized the energy dissipated as damage in the target plate was the strong-weak Nupperno configuration.
A strong hit first, weaker second.
With a time delay between the two hits of exactly 0.5 milliseconds.
0.5 milliseconds. Wait a second. That's right in the middle of the time window they measured for the cavitation bubble collapse after the main impact, right? 390 to 480 microseconds.
Precisely. The simulation independently found that the most damaging sequence was a strong hit, followed about 0.5 meters later by a weaker hit, which perfectly mimics the physical limb impact, followed by the slightly weaker, on average, cavitation collapse force.
That can't be a coincidence. The simulation confirms the shrimp's natural strike timing is, in fact, optimized for damage.
It strongly suggests it, yes. The system seems tuned not just for speed, but for the most effective sequential delivery of energy.
But why? Why is that 0.5 meters delay the magic number? What's happening in the target material at that specific moment?
The researchers proposed a fascinating hypothesis based on the target's own dynamics. When the first strong impact hits the plate, the plate doesn't just sit there. It absorbs the energy and starts to vibrate or oscillate, especially since it's fixed at the edges in the model, like a shell might be held or be part of a larger structure.
Okay, the first hit makes it wobble.
Exactly, and the simulation suggested that the 0.5 millisecond delay happens to coincide with a specific point in that oscillation cycle.
Which?
The point where the surface of the plate, right where the impact happened, is momentarily moving backwards, rebounding from the first hit. It's moving opposite to the direction of the incoming second projectile, or shockwave.
Wait, so the first hit pushes the surface in. It starts to spring back out. And at 0.5 meters, it's moving outward just as the second force, the cavitation, is coming in.
That's the idea. By timing that second hit to strike the surface when the surface itself has a positive velocity towards the impactor.
You maximize the relative velocity between the impactor and the target at the moment of the second collision.
Exactly. And energy transfer, especially damage energy, is often highly dependent on that relative impact velocity. Hitting something that's moving towards you is more damaging than hitting something moving away or stationary.
So the shrimp, or rather evolution, figured out the natural resonant frequency or oscillation period of the things it likes to hit, and timed its cavitation follow-up punch to land precisely when the shell is recoiling.
It looks like it might be exploiting the target's dynamic response. It's not just hitting hard, it's hitting smart, timing the second blow for maximum effect based on how the target reacts to the first.
That's next-level predatory evolution. It's weaponized physics timing.
Yeah.
Hashtag tag outro.
Wow, okay, so let's try and synthesize this deep dive into the mantis shrimp. It's given us two major insights for engineering, hasn't it?
I think so, yeah. Two really distinct but powerful blueprints.
First, there's the structure itself, that helicoidal architecture in the dactyl club. Copying that geometry in engineered composites like carbon fiber.
Gives you that huge boost, that 16 to 18% increase in residual strength after impact, plus much better resistance to internal damage, to delamination. It's a recipe for tougher, more damage-tolerant materials just by arranging the fibers differently.
Purely geometric optimization. And then second, there's the attack strategy. The strong weak double hit, timed at around 0.5 milliseconds. The simulation suggests this isn't random, but an optimized sequence to maximize damage energy transfer by exploiting the target's dynamic response.
It's lesson in kinetic timing, in how to deliver energy most effectively in sequence. So you have optimized defense in the structure and optimized offense in the timing.
It's a complete package, really. Durability and destruction perfected.
And for you, the listener, the relevance seems pretty clear. These aren't just curiosities about a weird shrimp.
Not at all. This points towards real engineering applications. Think about lighter, safer vehicles. Cars, trains, planes.
Composites that don't just save weight, but fail more gracefully. Ones that can take a bird strike on a wing, debris on the road hitting the underbody, and maintain structural integrity.
Exactly. Higher safety margins, more reliable performance, potentially lower maintenance costs if components can tolerate more minor damage. It impacts everything from aerospace to protective gear.
Truly bio-inspired innovation with tangible benefits.
But it also leaves us with a fascinating final thought, connecting back to the structure and the simulation.
Oh,
Well, we saw the Shrimps Club has that graded pitch in its helicoidal structure. The rotation angle changes through the thickness, likely optimized for the specific stresses in each region. Its defense is complex and locally tuned.
right. But the simulation results for the optimal attack timing, that zero point 0.5 meters delay.
Yeah.
The paper suggested that timing seemed pretty robust, maybe not super dependent on the exact target properties within their model.
Exactly. The zero point 0.5 meters delay worked best for maximizing energy dissipation against the target's oscillation.
So if that timing is robust, maybe the shrimp doesn't need to adjust its strike timing much, even if it hits different types of shells. It just uses the zero point 0.5 meters window provided by its cavitation physics.
That's one possibility. Nature optimizes for a generally effective strategy, but what if it could adapt? What if it hits something much softer or much thicker that vibrates differently?
Does it have some way to sense the target's response from the very first impact, maybe through vibrations felt in its arm?
And could it then subtly adjust the muscle contractions controlling that elastic recoil, maybe slightly delaying or advancing the strike to fine-tune that cavitation collapse timing, ensuring it always hits at the moment of maximum opposing velocity for that specific target?
So is it optimized for general durability and a fixed effective attack timing, or is it capable of specialized adaptive destruction?
That's the lingering question. How deep does the optimization go? Can it actively tune its weapons timing based on real-time feedback? That's a whole other level of biomechanical sophistication we're only just starting to explore.
From a tiny shrimp's hammer to the frontiers of material science and dynamic control. Absolutely fascinating. Thank you for joining us for this deep dive.
A pleasure. Until next time.